that occur in V, I and F due to the changes in the circuit. There are basically two types of transients, that is the switching transients and lightning transients, but the switching transients are more common in the transformer, and let's study about this in this class. Okay, basically when the switch is closed, the V and I undergoes disturbances. That is, consider a circuit like this. When the switch is closed, the voltage and I in this circuit undergoes disturbances, and this phenomena is called the switching transients. Okay, this severity depends upon the instant at which the switch is closed, that is T. Okay, so for example, if you consider the voltage waveform, so consider 2 points like this. Severity of the transient is different when the switch is closed at this point and when the switch is closed at this point, and let us see how. Okay, for example, consider case 1, that is V is equal to 0. Okay, this is this is the voltage waveform. Suppose if the switch is closed at V is equals to 0 instant, generally the flux waveform, okay, it is in this way. Suppose if the switch is closed at V is equals to 0, then what happens? Phi must start from this value, that is phi m, but the transformer is made up of a magnetic material, and since it has some magnetic inertia, it is impossible to attain the maximum value at the beginning point. So what happens is phi obviously starts at 0. Whatever first thing, irrespective of this case, that is irrespective of whether the switch is closed at this point or this point or this point, whatever it may be, phi always starts at 0. Okay, now this waveform, the phi starts in this way. It starts from 0 and it attains phi m, and it goes to a value of 2 phi m, and it starts like this. So this phi reaches a maximum value of 2 phi m, and it starts decreasing like this. It appears as if this phi phi flux waveform is shifted upwards like this by a value of phi m. So this is called doubling effect. Okay, so if the switch is closed at V is equals to 0, then we can observe the doubling effect. Okay, for this entire region the flux waveform is abnormal, and here it starts to be normalized. So we had a name for this period, and it is called, yes, transient period. Okay, so for example, now consider case 2. Okay, what if the switch is closed at V is equals to Vm? Then obviously again phi starts at 0 only, but here as you can see, the flux waveform, original value of the flux is also phi is equals to 0, and now again it is starting at phi is equals to 0, and it starts to increase in this way, and there will not be any doubling effect, but obviously it will not be the same, but still the doubling effect is minimum. It's like almost 0. You can consider it in an ideal condition. Okay, suppose if I consider case 3, say I switch on the circuit at somewhere between 0 and Vm, then again phi starts at 0, but here the original flux will be like, so the doubling effect will be moderate. Okay, see here the flux started at 0, but originally phi is equals to phi m, so this is giving you the doubling effect. Here the flux is starting at 0, and original also it is phi is equals to 0, and therefore there is no doubling effect. And here it is between 0 and phi m, and the flux is starting at 0, so the doubling effect is moderate somewhere between these two cases. Okay, so now I'll explain you the main problem. As we know the EMF equation of the transformer. Now what happened in this case, the flux is doubling, means it is like twice, so this 2 is implied here, and this gives you the double EMF. So EMF is also doubled. But as you know, the transformer winding is purely inductive. In order to minimize the losses, we always choose it to be less resistive. And so if we find out the time constant, it is L by R. This L is so high and this R is so low, so obviously this transient period occurs for a very less time, and this time constant of the transformer is very high. So obviously at the time when the transformer is ready to react to the disturbances, that is, at the time when the transformer is ready to react to the disturbances, the transient period is already over. So what happens is, where is this double EMF is being induced? Yes, that is the point. Due to this time constant, the dielectric stress is increased in the end portions of the winding. Okay, say if you consider this as the winding, say, see, this is the core, this is the winding. So the dielectric stress is increased at these end portions. Okay, so what happens is this EMF is induced at this area, and what happens is so the EMF is induced in this area, and it results in the localized damage in the form of puncture, in turn it causes the fault in the transformer. Okay, in order to avoid this, what we do two things. One is reinforcing, that is the end portion, this portion is made in this way, that is extra thickness is added at the end portions of the winding, so that it can tolerate the excess EMF induced in it, so that it will not damaged. So generally this is employed in LV transformers. And the second thing is grading. Okay, suppose if you consider the winding in this way, so if we use class E insulation for the transformer winding, generally the endings it is graded like this, E, F, G, where G is superior, so that it can tolerate more temperature rise and more voltage. So the G is superior than F and F is superior than E. So therefore we are adding extra strength to the end portions of the transformer. So in this way we are avoiding the localized damage that occurs in the end portions of the transformer due to the dielectric stress which is caused due to the switching transients in the transformer. So in order to avoid this dielectric stress in the end portions of the transformer winding, that is almost 80% of these impulse EMFs are induced in the 5% of the extreme end winding portions rather than the complete winding. These impulse EMFs are non-uniformly induced in the winding. These impulse EMF levels decreases as we go to the inner winding. So we have to design the transformer in a way such that it can withstand these high flux caused due to this doubling effect, and so we have to go for either this reinforcing or grading. Also, let us observe one more point. So till now we have studied about the variation in the voltage and current, and let us see about this. See, so this is the flux waveform. This is phi m, and this is 2 phi m. Okay, this is I mu normal, it is the magnetizing current, that is it is generally the 5% of full load current, and this is the I mu transient. This is almost 50 times I rated. Okay, so I mu normal, say if it is 0.05 per unit, because it is 5% of the full load current, and I mu transient is 50 times this, and this gives you 2.5 per unit, that is 2.5 times of the rated current. So these are called the magnetic inrush of currents. This inrush of currents means large amounts of currents are rushed into the primary, and this magnetic is because it is a magnetizing component of the current. Okay, so in normal conditions this I mu is neglected, but what happens during these abnormal conditions is, see, if you consider the transformer winding like this, here you have the conductor, this is going inside, means this is coming outside, and this will be obviously opposite way. So in normal conditions I naught is neglected, and therefore this N1 I1 is equals to N2 I2, and net force is 0. But here therefore there is no dislocation of the windings, but in this case what happens is this N1 I1 is more than N2 I2, because this magnetic inrush of currents are induced in the primary at a very faster rate. Okay, and therefore the forces are unbalanced, and resultant force is not equal to 0. This means the windings are not mechanically stable, because there is a radial force on these windings like this. So this winding is pulled in this direction, and this winding is pulled in this direction. See, suppose if you apply the left hand rule, this is going like this, and the force direction is in this way, and if you see for this winding, the force direction is in this way. Similarly for this also, the force is in this, and for this it is in this way. Therefore there are the radial forces acting upon the transformer windings. Okay, so this windings are not mechanically stable, and external mechanical support is needed to avoid this mechanical dislocation of the windings. So as we can see, this is the representation of magnetic inrush currents, that is, this is the I mu waveform, as we can see when a transient is occurred, and the I mu attains a very high value, and it starts decreasing as the transient period is coming to an end, and then it obtains its normal waveform. Okay, so this part we call it as a transient period, and this is the normal period. Okay, as you can see, this is the DC component of this I mu. Initially the negative wave of the I mu is absent. For flux during one cycle it is unidirectional. In order to produce in order to produce the flux in unidirection, the core is also magnetized in only one direction, and it results to saturation. The current is also unidirectional because it is a DC component, right? Also AC component is also present, and DC component is also present. This DC component is absent during normal operation. See, due to this transient occurred, the extra part is this DC component added to the waveform. As you can see, in this region, the DC component as well as AC component both are present. But in normal condition, the DC component is 0. Okay, this is called the DC offset current, okay, which is not symmetrical about x-axis. This means the Fourier series not only contains odd harmonics but also even harmonic currents, okay. As we know, the fundamental component is 1, odd components are like 3, 5, 7, and even are 2, 4, 6, 8, 10, whereas this 2 is the dominant harmonic, okay. So this magnetic inrush currents is rich in this second harmonic component, whereas magnetic harmonic currents are rich in the third harmonic, okay. Just understand the difference. There are two types, that is magnetic inrush currents, harmonic currents, okay. This is rich in second harmonic and this is rich in third harmonic, okay. So with the modified design of the transformer, that is either the graded or reinforced or the adding an extra steel channel support to reduce the mechanical imbalances in the transformer winding, the transformer is need not to be tripped unnecessarily. Generally this high current results in the tripping of the transformer circuit, thinking that it is an fault, but no, this is not a fault, right? So the transformer should not be tripped unnecessarily during the switching of the circuit. So see, unnecessarily the transformer is stripped from the circuit during switching itself due to the high magnitude of this inrush currents, which is undesirable. Hence, we should design the protection circuit in such a way that it can distinguish between these fault current and this magnetic inrush currents by using second harmonic restraining coil, okay, as I call it as RC, okay. This is used for biasing. The fault currents does not contain the harmonics, whereas the magnetic inrush currents contain the second harmonic dominantly. So the second harmonic restraining coil offers less impedance to the flow of the second harmonics. Hence, it is energized due to this second harmonic currents, and tripping does not take place during the transient, okay. But during the fault conditions, the current does not flow through this restraining coil because the differential current does not flow through this restraining coil. The differential current flows through the operating coil and it trips the circuit. So if the restraining coil is activated, the negative action on the operating coil, that is no operation of the circuit breaker tripping. If the restraining coil is inactive, that is in case of the fault conditions, no action takes place in the operating coil, that is the relay operates to trip the circuit. So this is how it happens in the transformer when there are transients, that is switching transients in the transformer. I hope everything is clear. That let me give it a glance. When you are switching the circuit, when you are switching the circuit in which transformer is present, switching disturbances occurs in the voltage and currents, and the severity depends upon the instant at which you are operating the switch, and it is mostly desirable to switch it on when V is equals to V max, because at that point the doubling effect is zero, that is the flux is not doubled, whereas in the other cases the flux is very high, which results in the doubling of EMF, and due to this doubling of EMF, this extra EMF cannot be induced in the entire winding due to the high time constant of the winding. So there is a dielectric stress in the end portions of the winding, and to avoid this, either we go for the reinforcing of the transformer winding or grading of the transformer winding. And the other thing is, due to this high magnetizing current of the transformer, due to this switching, generally the I mu transient is very high than the I mu normal, and this is called the magnetic inrush of the currents, and this results in the mechanical imbalance of the transformer windings. And also due to this high current, the circuit might mistake this switching for a fault, and it might trip the circuit during the switching. And in order to avoid this, we will incorporate a second harmonic restraining coil, because this magnetic inrush currents mostly contain of a dominant second harmonic currents, whereas it is absent in the normal operation. So I hope it is clear, and if you have any more doubts, just comment down in the comment section. And if you like this video, just give it a thumbs up, and if you feel it is useful and understanding, just share with your friends. And for more videos, just subscribe to my channel and stay updated. Thank you for watching.